Okay, so today what we're going to do is we're going to talk about multiple interval pseudospectral methods because I want to go over a little bit about how you actually use some of this stuff in a more realistic situation. The theory that I had done earlier was for single intervals, where you assume that the collocation was done by starting with a global polynomial. And what I want to do today is I want to take one lecture, and this may extend to the next lecture depending upon, how valuable this is. I'll ask everybody after class, to go into to more details on it. But let's go back. So if you recall the three sets of Gaussian quadrature points. Which are 1, Legendre, Gauss. Second is Legendre, Gauss, Radau. And the third were Legendre, Gauss, Lobato. Now, if you remember, if I draw a schematic of these, I've got LG, LGR, and LGL. If you remember that the LG points, if I draw the line, the number line, from -1 to 1, that the LG points only included values in the middle and the interior of the interval. And so -1 and 1 are excluded. They're not included in the set. In the case of LGR, if I just use the forward LGR points, not the backward LGR points, you've got -1 to 1, and now -1 is actually included as one of the LGR points, but +1 is not included. So this is open. So +1 excluded. And this was tau on this, right? And then we had LGL, where it included both endpoints, and then there were points in the middle. I'm drawing this schematically, so -1 and +1 included. Now, the theory behind this was that the points, because they come from a high accuracy quadrature rule, could be used to generate approximations to the solutions of the optimal control problem by replacing the cost functional with a quadrature approximation and then replacing the dynamics with a set of algebraic equations that form these collocation conditions based on the state approximations, right? So we had state approximations that for these two, I'll just write them out just so that we refresh our memory, which was that if I let tau 0 equal -1 and tau n plus 1 equal +1, then the state x of tau was approximated by some function capital X of tau, which is the sum from I equals 0 to n. Oh, well, I'm running out of room here, so let me, it's on the next line. Which is equal to the sum from I equals 0 to n of xi Li of tau, where Li of tau were the Lagrange polynomials, where you go from j goes from 0 up to n, j not equal to k, tau minus tau j, tau k minus tau j. So it's j not equal to I. Okay, so that took care of LG. I'll draw a line here so we don't get confused. LGR, tau 1 was equal to -1, and tau n plus 1 was equal to +1. and we had that the state was approximated by some function x of tau, which was the sum from I equals 1 to n plus 1, xi li of tau. And in a similar manner, these Lagrange polynomials were the product from j equals 1 to n plus 1, j not equal to I, tau minus tau j over tau I minus tau j. And then we had LGL, where tau 1 was equal to negative 1, and tau n was equal to plus 1, and x of tau was approximated by capital X of tau, which is equal to the sum from I equals 1 to n of xi li of tau. And in this case, li of tau was the product from j equals 1 to n, j not equal to I, tau minus tau j, all divided by tau I minus tau j. Okay, so that was a summary of this whole thing. Now, if you want to solve a more practical problem, see, global polynomials, so what did we do in the original formulation? In the original formulation, or in the global formulation, what we did was we took the time interval from t0 to tf, and we transformed it to negative 1 to plus 1, right? So we started with the problem on t0 to tf, and then using a global polynomial, which is one of these polynomials that I have up there, we transformed the whole thing to negative 1 to 1, and then we rewrote the problem in terms of negative 1 to 1. Of course, the problem with this is that if you're using a global polynomial, so the trouble is that global polynomials may not suffice. In fact, they usually don't. Because think of simple problems where you could have trouble with a global polynomial. For example, if you have a problem whose solution is bang, bang, the optimal control is bang, bang, right? You have a discontinuity. If I'm approximating a problem whose solution is not smooth with a polynomial, where's the problem going to lie? The problem is going to lie in the fact that a polynomial is a smooth function, right? No matter how high a degree polynomial I take, I'm always approximating the solution with a smooth function, right? So you get this thing called Gibbs phenomena, and the Gibbs phenomena looks something like this. If you had a problem, let's say the solution looked like this, it was bang bang. What would happen is, for a low degree approximation, you get something that kind of looks like that. And then as you increase the degree of the polynomial, you're going to get something that's going to look like this. And if you keep increasing the degree of the polynomial, you're going to get things that are going to look more like, they're going to look kind of like what you expect. But at the point of the discontinuity, you're going to get this huge jump in the error because you're approximating something with a smooth approximation. This is exactly what happens with a Fourier series. If you remember anything about Fourier series, if you try to approximate a square wave with a Fourier series, if you truncate the series anywhere, at the point of the discontinuity in the square wave, you get this huge jump in this huge error in the solution because you're trying to approximate it with a smooth function because you're replacing the approximation with a series of sines and cosines, and sines and cosines are smooth functions, but the function you're trying to approximate is itself not smooth. So unless you retain all, quote, infinity terms, I put that in quotes because nobody retains the entire infinite series, you can never accurately approximate the square wave in the region of the discontinuity with a finite series. So that's exactly the same thing that happens here because these are all finite series. If you look at them, right, they're all finite series. So the way you have to deal with this is to break the problem or divide problem into intervals. Now we've talked about this before in the context of like multiple shooting, but what I'm talking about here is slightly different, all right? Divide problem into intervals and perform collocation over each interval. Now let's look at this. Let's look at this in a slightly different, in a simple way, and then we move to something more general. Let's suppose we take the case of LG points. Okay. And, well, before we write that down, I meant to write something else down. Consider a problem divided into two intervals. Okay, so what I'm doing here is I'm taking T0 to TF, and I'm going to divide it at some point T1. That's all I've done. Okay. Now, and let's suppose we're going to use each of these collocation schemes in that on each interval separately now, right? So how am I going to do this? What do I have to do? I've divided the problem into two intervals, and let's just assume for right now that that point T1 is fixed. Okay. So I've set it. I'm not changing it. Okay. T0 and TF may change, but T1 doesn't. All right. And even if you want to make it simpler, assume T0 and TF are fixed because it will make this thing a little bit easier. So how are we going to do this? What is it that we need to do? Well, if we want to do the collocation across each interval, what I would need to do is I would need to apply that scheme that I used over there, whichever one I choose, across the first interval, and then apply one of those schemes across the second interval. The question is, what is that going to lead to when you actually do this? So let's look at what happens with LG points, okay? And then we'll look at LGR, and then we'll look at LGL. So for LG points, what I'm going to get is I'm going to have one interval where the LG points go from -1 to +1. I'm going to have a second interval where the LG points go from -1 to +1. And right here, I have to have continuity in the state. State has to be continuous. It can't be a discontinuous quantity. It's required that it be continuous, okay? So what I get here, if I look at the diagram, you see that the LG points are here. Here's my initial non-collocated point. Here's my final non-collocated point. And in the second interval, I have the same problem. I have the same issue. I've got the LG points in the middle, and I've got two non-collocated points. Now, the trouble with this is that you can see that the control in the first interval is only approximated at the LG points. Similarly, in the second interval, it's only approximated at the LG points. There's no control, or there's no value of control here, because the LG method only allows you to be able to approximate the control at the LG points, because that's the way the scheme is set up, right? So now look what happens when you do this with LGR. Now, I'm going to switch this in just a minute to something a little different, but I want to show it to you this way first. With LGR, I've got two intervals. Again, -1 to +1, -1 to +1. And now the LGR points, if you remember, include this initial point, but don't include the final point, right? The second set of LGR points includes the initial point, but don't include the final point. Now, what's true about the control now this, remember, continuity has to be met. State must be continuous. Okay, so what happens in the case of LGR? In the case of LGR, I don't have a collocation point at the end of the first interval, right? Because even though the state is approximated there, there's no collocation there, which is why I've drawn it with a square. But there is a collocation point at the beginning of the second interval, right? And since the state has to be continuous, what I can actually do is I can collapse this. This is hard. It's hard to do it when you break everything up in -1 to 1 and -1 to 1. But I'm going to schematically show you what it looks like and just drop the time values for just a minute, just so you can see. Which is what I have is I have this. If I assume that these two variables are the same, in other words, the value of the state at the end of the first segment and the value of the state at the beginning of the second segment are the same variable, right? Because they're equal to each other, so I can set them equal to the same variable. What I'm actually going to get is I'm going to get this. I'm going to get this is the start of the second interval. So what I'm going to get is I'm going to get something that looks like this, and then I'm not going to have a control here, right? Because I don't have a control at the end of the first interval, right? But I do have a value of a control at the beginning of the second interval. So at the start of the second interval, what I've got is, if I like put this in with a diamond here, the start of the second interval has everything that at the end of the first interval wasn't collocated. It's now collocated at the beginning of the second interval. So I have control everywhere here except for at the final point. So there's no control here. Right? But there's a control value here because it's the control that corresponds to the value at the beginning of the second interval, right? So now let's look at the last scheme, which is LGL. Now with LGL kind of has the opposite extreme from LG, which is that if I start with this negative 1 to 1 and negative 1 to 1, and again, I've got continuity in the state, then look what I have here. I've got collocation points throughout everywhere, including the endpoint. I've got collocation points here, including the endpoints. Now, what's the difference between this and what goes on with LGR? The difference is I have a value of the state at the beginning, at the end of the first segment. I have a value of the state at the end of the second segment. I can make them equal to each other, right? Just like I can with LGR. The trouble is I actually have two values of control, right? Because I have a control here, control at end of segment 1, and I have control at the start of segment 2. So the trouble is, with the control, I have a double-valued control, right? Double-valued meaning that there's a value that comes from the left and there's a value that comes from the right. There's no requirement that they have to be equal to each other, right? I don't know whether they're equal to each other or not because I don't know whether my control is continuous before I solve the problem, right? If I solve a problem for which the control should be continuous, I should get one solution. If I solve a problem for which the control is discontinuous, I'm going to get a different solution. But the problem is that these two values of the control occur at the exact same point in time. And so the question is whether or not you should set them equal to each other or whether you shouldn't set them equal to each other. In the case of Redao, you never have to make that choice, right? Because in the case of Redao, there is only one value of the control at every single point in time. There are no double values, right? Because the control never overlaps. This control actually overlaps in the case of Lobato. It turns out that this is the most natural of the schemes to actually consider. So I'm going to do this. I'm going to do Redao. This is the reason why when you actually go through this progressively, you actually find that this makes the most sense. There are two reasons why this makes the most sense. One is the structure is really, really nice. But the second thing is the fact that, remember, I derived the fact that these two schemes are both Gaussian quadrature integration schemes, and that's not a Gaussian quadrature integration scheme. So when you do this, you have either one of these is going to give you the same amount of accuracy. The difference is, though, that there's no value of control at the interface point in Gauss, right? So you lose information in the process of using Gauss. You can't get a control at that interface point. Whereas with Redao, you get that, and you get it in a non-overlapping manner. So let's go through this for Redao. So in order to do this, we actually have to do this a little differently from the way I just said. So the way we do it, we do this in two steps. And this is a little bit non-intuitive at first. So you're going to have to ask me questions if you are confused, because I could imagine anybody being confused by this. So let's look at the multiple interval Redao method. Now the way we're going to do this is as follows. Is you remember that originally we had t was between t0 and tf, right? So if I do this transformation to get myself on negative 1 to 1, if you remember the steps that I did, I took t, I subtracted t0, I got myself on 0 to tf minus t0, which then gives me 0 is less than or equal to t minus t0 over tf minus t0, which is less than or equal to 1, which gives me 0 is less than 2 times t minus t0 over tf minus t0 is less than or equal to 2, which gives me minus 1 is less than or equal to 2 times t minus t0 over tf minus t0 minus 1 is less than or equal to 1. And that's what I defined to be tau. But what I'm going to do now is I'm not going to define this to be tau. I'm going to define this to be s. It's a new variable, okay? So s is on the interval -1 to 1. All right, now, the question is, how is this any different from doing this with a global method? Well, the way it works is as follows, is that now I have this domain -1 to 1. Just like I did when I transformed the problem originally. I'm just not calling it tau anymore. I'm calling it s. The reason I'm calling it this is because I don't want you to get it confused with the global method, okay? Because in the global method, I called everything tau. I want you to understand this is a segmented method, which is hence the name s. That's why I use s for segmented, okay? So now what we have is, we have s on -1 to +1. So if my optimal control problem, if you remember the original optimal control problem, looked like this. It was J was phi of x of t0, x of tf, plus the integral from t0 to tf of L of x u t dt. The dynamics were x dot, which is the same thing as dx dt, is equal to f of x u and t. And then we had some boundary conditions, phi of x of t0, x of tf, and tf is equal to 0. And then we had some path constraints, which was c of x, u, and t were between some c min and c max. So now what we're going to do is this, is if I transform that to the time interval -1 to 1, where I use s as the variable of transformation, what I get is this. So transforming to s, which is a -1 to +1, we get the following problem. We get j, which is equal to phi of x of -1, t0, x of +1, tf. And then I got plus tf minus t0 over 2 times the integral from -1 to +1 of L of x of s, u of s, s, t0, tf, ds. And then I have dynamics, which are dx ds is equal to tf minus t0 over 2 times f of x of s, u of s, s, t0, tf. And my boundary conditions are phi of x of -1, t0, x of +1, tf is equal to 0. And then c min is less than or equal to c of x of s, u of s, s, t0, tf is less than or equal to c max. Okay, so that's the transform problem. Okay, now, if you look at this problem, you'll see something about it. You remember this is the same problem that you get when you transform the optimal control problem first. Remember when I did the pseudospectral schemes, I actually started on the interval -1 to 1, right? I did this Mayer problem, right, where the cost was phi of x of +1, and then I just had dynamics dx d tau is equal to f of x and u, and I did everything on -1 to 1. So you notice in the sort of more pedagogical problem that I did, I didn't have the scale factor of tf minus t0 over 2 sitting in front of everything because I assumed the problem was already on -1 to 1. Here I'm not assuming the problem's on -1 to 1. I'm saying it's on t0 to tf and transforming it. And the reason that transformation comes into being is really simple. If you look at this right here, you'll see that s is equal to 2 times t minus t0 over tf minus t0. So if I take ds dt, what do I get? So ds dt becomes 2 over tf minus t0, right? So dt ds becomes tf minus t0 over 2, which is where that tf, all those tf minus t0s over 2 come from in those equations right there. All I've done is just transform the variable, and by doing that, I've put this on the interval -1 to 1, and I've introduced the scale factor. Now, in the process of this, we should say where we note that T0 and Tf are parameters in the problem, if they're in fact where I said that if T0 or Tf is free, then you solve for that as part of solving this problem. Now, if you look at this, you'll see what I've done is that I'm now going to work on the interval -1 to 1. I'm not going to work on the interval from T0 to Tf and break it up. I'm going to take on the interval -1 to 1. So what we do is now consider the interval -1 to +1. Why can I consider that? Because everything here is on the interval -1 to +1. So that's the only thing I need to worry about, right? So what we do is we take this interval -1 to +1, and this is now S here. And what I do is I divide it up into a bunch of intervals. Suppose I call this S0. I call this S capital K. This becomes S1, S2, S3, all the way up to Sk minus 1, and then this becomes Sk. So what we've done is now we've said that the interval -1 to 1, which is a fixed known interval, right? There's nothing unknown about it. I don't have an unknown T0. I don't have an unknown Tf. They've been absorbed in these other quantities over here, right? T0 and Tf are still surely in the problem. They're not gone from the problem. They just appear in different places, right? L may be a function of T0 and Tf. The right-hand side is a function of T0 and Tf. But the interval over which I'm doing the computations is fixed at -1 to 1. It's always on -1 to 1. Okay? So what this allows me to do is, it allows me to lay these points down. So what I say is where S0 all the way up to Sk are called mesh points. And what I've done here is I've constructed a mesh. So this is a mesh, all right? So this mesh that I've constructed consists of fixed points, right? Are called mesh points, such that all mesh points are fixed. When I say they're fixed, I mean somebody has to choose them. They say, I'm going to choose these to be the mesh points, and then I'm going to fix them at those values. They're not variables in the problem. They cannot vary, right? I can pick them to be whatever I want them to be, but once I pick them, then they're specified, right? Then what you do is on each mesh interval, Sk minus 1 to Sk, we perform Radau collocation. What does that look like? Well, it looks like this. So the state approximation in interval Sk minus 1 to Sk looks like this. It's Xk of S, which is the solution in the kth mesh interval, is going to be approximated by some function capital Xk of S, which is going to equal the sum from k equals 1 to n sub k. I'll define n sub k in just a second. It's an n. N sub k. Right? Of x. Xi Lik of S. And you can be careful, it's Xik. All right? So now what I've done is I've said that in the kth mesh interval, wherever that happens to be, somewhere here, right? So I've blown up this interval, here's sk minus 1. Here's sk. All right? In this interval, I'm saying xk of s is being approximated by capital XK of s. Okay? Now, if you look at this, you'll see that there's no difference between this approximation and the original LGR approximation that I started with, right? The original LGR approximation went from 1 to n plus 1, right? And I had one interval, which goes from -1 to 1. Here, I'm doing the approximation to go from 1 to n sub k plus 1, where n sub k is equal to the number of LGR points in sk minus 1 to sk, right? So I can choose these to be any number of points I want them to be, right? Because how many LGR points I choose in an interval is also up to me. I can choose where the mesh points go, and I can choose the number of LGR points in the interval itself, right? Now, the difference is, though, that if you remember, I started with -1 to 1, and I broke it up into a bunch of intervals. So the LGR points in this case are not defined on -1 to 1. The LGR points are defined on sk minus 1 to sk. So you have to keep that in mind, too, where the n sub k LGR points are defined on the interval sk minus 1 to sk, right? Now, if you look at that, if these points were not fixed values, I would not be able to define the LGR points because the domain of the LGR points has to be fixed, right? The original domain of the LGR points was -1 to 1, right? So -1 and 1 are both numbers. Fixed, they're constants, right? Because last I knew, -1 and 1 were constants. You can only define the LGR points on a fixed domain. So these have to be fixed quantities, because if they're not fixed quantities, I can't define the LGR points. How do I define the LGR points on sk minus 1 to sk? That's actually fairly straightforward, but may not be obvious. Okay? Which is that we know that the LGR points are traditionally defined on tau in -1 to +1. Notice, that's why I didn't use tau over here, okay? I don't want you to get confused with what I called tau before with what I'm calling s now. They're not the same thing, all right? They're different, right? So I know that tau is on -1 to +1, which implies that -1 is less than or equal to tau is less than or equal to +1. So now let's do this. So now that means 0 is less than or equal to tau plus 1 is less than or equal to 2, right? So if I take this, this tells me that 0 is less than or equal to tau plus 1 over 2, which is less than or equal to 1, which says that 0 is less than or equal to sk minus sk minus 1 over 2 times tau plus 1, which is less than or equal to sk minus 1, which says that sk minus 1 is less than or equal to s sub k minus sk minus 1 over 2 times tau plus 1 plus sk minus 1 is less than or equal to sk. So there's my transformation right there. So what it says is, if I compute the LGR points on -1 to 1, the way that I would normally compute them by using the standard LGR points, which are -1 to 1, I can transform the LGR points to the interval sk minus 1 to sk via this transformation. Notice it's the same transformation that I had over there. There's no difference. It's just the inverse of it, right? I mean, this goes from T0 to TF back to -1 to 1. This goes from -1 to 1 to sk minus 1 to sk. But sk minus 1 and sk are fixed values. So if I have the LGR points on -1 to 1, all I need to do is plug every single one of those values in here, and I get the LGR points on sk minus 1 to sk. Does that make sense to everybody? Yes? No? Yes? No? Does it not make sense? Okay. So now what we do is, given the fact that we've done that state approximation and we can compute the LGR points on sk minus 1 to sk, now we can replace some things in this optimal control problem with approximations, which is that, so we know that the integral from -1 to 1 of g of s ds is equal to the sum from k equals 1 to k of the integral from sk minus 1 to sk of g of s ds, right? I haven't done anything fancy there. Right? I just took the interval and just broke it up and just added up all the integrals, right? I can do that, right? So now I know that this integral can be approximated by Redao quadrature. So I get the sum from k equals 1 to k of the sum from I equals 1 to n sub k of g of si k times w k I. Right? All I did was I took each one of these. I know the Redao points, so I can compute the Redao weights too, right? I mean, the Redao weights go along with these Redao points. So I've got these Redao weights, where WIK are the LGR weights on SK minus 1 to SK. So now what I can do is I'm gonna keep that board. I'm gonna erase this board. I'm not gonna erase that board because I need the equations. So what I get is, so then the cost functional can be approximated using an LGR quadrature as I get J is approximated as phi. Now, what has to go in here? X of -1. This is S equals -1, right? So that corresponds to the state approximation evaluated at -1 in the first mesh interval, right? The first mesh interval is which mesh interval in this case? It's going to be S. It's going to be at 0, right? So this is going to correspond to the value of the state X at what? 1 in mesh interval what? 1, right? First mesh interval, the initial value of the state, because x1 is the initial value of the state in that approximation, right? And then I've got t0, and then I've got x n sub capital K. Be real careful here. This is a capital K, right? Plus 1 in mesh interval capital K, and then tf, right? This is a capital K. Okay? So is this. All right? Plus the sum, right? Now I got to be careful here. Let's put the tf minus t0 over 2 in front of this whole thing. So I've got tf minus t0 over 2. And then I've got all these summations here. I've got the sum from k equals 1 to capital K of the sum from I equals 1 to n sub little k of L of x I k u I k times w I k. Yes? Now the dynamics in each interval, I'm skipping this board. So the dynamics in each interval, if I take the derivative of that state approximation, so we know that dxk of s ds is going to be approximated by whatever that is, which is d capital X k of s ds, which is going to equal the sum from I equals 1 up to n sub k of x I k times d l I k of s ds. So then what I do is I collocate that at the n sub k LGR point. So collocating at the n sub k LGR points, we have the following result, which is that the sum from I equals 1 to n sub k plus 1 of x I k times d l I k of s ds evaluated at I is going to equal tf minus t0 over 2 times f evaluated at x I k u I k s I k and then t0 and tf. Okay, where these right here, you have to be real careful with this. D L I k of s ds evaluated at, let's be real specific here, it's evaluated at SIK. SIK is equal to d ki in k, which is the Radau differentiation matrix in sk minus 1 to sk. I'm not going to finish this today, but we'll set this whole thing up. Okay? Everything else stays exactly the same. The path constraints look exactly the same. What goes in here is exactly the same thing that's used to approximate this up there, because they're functions of the exact same quantities. There's no difference, right? So if whatever I have in the Mayer cost, that's exactly what goes in these boundary conditions. And then as far as these over here, you get exactly the same thing. So let's just write that out just to see what I want to keep. I need to keep this. So the boundary conditions are approximated and we get phi, and we get the exact same thing. We get x1 of 1, t0, x n sub capital K plus 1 of k tf is equal to 0. That's exactly the same thing that I have here. And then the path constraints we've got C min is less than or equal to C of x I k u I k and then s sub I k t0 tf is less than or equal to C max. And this goes from k going from 1 up to capital K, and I going from 1 up to n sub little k. So that gives me my discretization. Now what's nice about this discretization, which I don't have time to talk about today, we'll do it on Wednesday, is that it winds up stacking up in such a way that when you're all done with the discretization, you can apply it the exact same way you would have applied the global Radau method. It looks mathematically exactly the same, with one exception. The one exception is that the differentiation matrix now is not a big full block. It's a block diagonal. But I'll go into that next lecture because I don't have enough time to go into all that structure today, all right? But this is the starting point, so this is good. So we'll pick this up on Wednesday and we'll finish this up, and then we'll talk about how you actually choose the mesh and what you can do to minimize error and things like that. That's next lecture, okay?